Good afternoon. How's everybody's Ignite going so far? Good? Hope you're hearing a lot of interesting stuff. I had a good time listening to Rohan Kumar's keynote. That's kind of the area of the org that we both work in. My name's Kevin Farley. I'm a principal program manager in the data platform team. I've been in the SQL org for about 14 years now, so I've seen a lot of things come and go. With me is Shri Chinchala. She's one of the developers in the query processing team, so it's really cool that she gets to come out here and talk about the stuff that she made. So what we're going to talk about is some features within the query processor, within the SQL engine, that are making it more intelligent and more adaptive, so it can respond to the conditions that it sees and self-tune. I'm going to start with talking about adaptive query processing. This is a set of features that we brought into SQL 2017. And they were more strictly adaptive. So they dealt with adapting to the situations that it saw. So if it was missing estimations, making wrong choices, it would adapt and correct itself. So query processing has getting good efficient queries, getting good performance has a lot to do with cardinality estimation. So that's the art or science of predicting from a given query how many rows are going to flow out of each of the tables and through each of the branches within the query plan. So during optimization, cardinality estimation is responsible for estimating the number of rows at each step in the query plan. Uses a combination of statistical techniques and assumptions. So we have statistics associated with tables that are histograms. So for various values, we expect this many rows. It's sampling. It's an estimate. It depends on how detailed you choose to make the sampling. And then there are assumptions. So for certain constructs, we don't have knowledge of exactly how many rows are going to be flowing. So we make assumptions. Some of them are good. Some of them are not so good. And part of this work is fixing some of those where the assumptions are not really as valid as they might be. When estimates are accurate enough, we make good decisions about order of operations and physical algorithms. So we get the right plan, and you get your data back fast. So why do we get incorrect estimates? Missing statistics. So those statistic histograms that I talked about can either be automatically created or they can be manually created depending on how you set things up. If you have them set for manual creation and you haven't created statistics on a table, then we have no way of knowing how many rows to expect. So we'll guess something blindly like 100 or 1, and the plan will get optimized from that. Stale statistics. So if you are using manual statistics and you haven't updated them in a while, then the content of the table may not be reflected by the statistics. Or if you're using automatic statistics and you've recently done something that changed the shape of the table significantly, like done a big data load or pruned a bunch of data out of it, again, the statistics may be out of sync with the content of the table, but we'll believe the statistics when we go to optimize the query, and we'll probably make some wrong decisions. Inadequate statistic sample rate. So when you set up statistics, again, it's a histogram of values, and you have control over how fine-grained that is. And the ultimate is to do a full scan of the table, so you sample every possible value. And the coarser you get it, the faster it runs, the less overhead it is, and the more chance you have of missing spikes in the data. So if you measure here, and there's a spike in between, we'll miss it. So that's kind of the trade-off in what setting the sample rate for your statistics is that there's overhead involved in having a really fine-grained sampling rate, but then you're going to catch more anomalies in the distribution. Who's heard of parameter sniffing problems? So parameter sniffing is a phenomenon which causes us no end of headaches. When you have a query that runs on parameters, we will typically optimize the first time we see that query. We'll optimize based on whatever value happened to be passed into it. The next time we see that query, because the query text just contains the variable for that parameter, we're not going to re-optimize because the query text hasn't changed, but the value coming in may be completely different. So if the value that happened to be used the first time that query was run was very typical for the values you'll see the rest of the time, then you get a nice performance overall. You may see one or two anomalies, but the overall performance is going to be fairly good. If it happens that the first time you run that query, you have a value that's way off from the normal, then we're going to optimize to that value, and the common case is going to be way different, and so you're going to have a lot of problems. We've actually got a demo of that in a bit. Out-of-model query constructs. So there's an amazingly complex piece of code in the optimizer. It's stunning to me, and I've been around it for a while. But for different constructs, we make assumptions as to how they're going to behave. And there's some constructs that we just don't have good models for. And so we'll make guesses. Some of them are like, for multi-statement table value functions, historically the guess has been 1, just because. One of those constructs for the new query estimator, cardinality estimator that came along in a couple of releases ago, we changed one of those from 1 to 100. It seemed a little bit more valid. And assumptions not aligned with data being queried. So if you're doing a join, there's this independence versus correlation. So if you have two variables, say state and city, we know that those are correlated. So if you have a state and a city, there's bindings there. Chances are if you have the city named Los Angeles, the state is going to be California, right? So there's a correlation there. Other variables aren't correlated at all, and that has a lot to do with how we set up the query plan. So any of those things, we're going to guess wrong about how many rows are going to come out of that join if we guess wrong as to whether they're correlated or not. So all those things can cause problems with cardinality estimation. And that's what a lot of this is going to be doing. So the cost of incorrect queries, slow query response time due to inefficient plans. So we didn't set the plan up right because we optimized for data you don't have. Excessive resource consumption. So if we optimize for very large values and you've only got a small amount flowing through, then we will have set up the data structures to support that very large set of data. We will have grabbed lots of memory, and then you're going to waste all that memory. Or conversely, if we optimize for a very small set of data and grab enough memory for just a small set, and you throw 5 billion rows through, then we won't have enough space to cache all that, and we're going to spill data to TempDB, and things get really slow then. Spills to disk. That's an example of that. Reduced throughput and concurrency. So if we're grabbing too much resources, more resources than we really should for a given query, that's going to starve all the other queries that are trying to run. T-SQL refactoring and off-model, to work around off-model constructs. So we see T-SQL that has been tortured into conformations that'll work around the fact that we don't optimize certain constructs well. So people will work around those constructs and get their query to run, and actually it'll be faster even with that convoluted code than it should have been if we had done things, if we had recognized that construct. So one of the features that we introduced in 2017 was interleaved execution for multi-statement table value functions. That's a mouthful. Multi-statement table value functions are tracked as a black box. They're given a fixed optimization guess as 1. So if you have multi-statement function that yields a table as a value, and then that table is then used in a query, we don't have a good visibility into what it took to get to that table, and we'll just guess 1. So what we did in 2017 is we broke the pattern. Forever and ever, the pattern of query processing has been you optimize, you look at the query, you look at the statistics, you optimize it, and then you execute. With interleaved execution, we actually interleave optimizing and execution phases. So multi-statement table value functions, that makes a really clean boundary around a small corner of the query. So we'll optimize up to that point. We'll execute until we've gotten the values for that table value function and use the cardinality from that, which is actual, going to be really precise, and use those cardinality estimates for the rest of the query. So multi-statement table value functions was a really clean first case to tackle, and it's worked really well. So you can expect us to take on more different constructs that behave in similar ways, where we'll take corners of the query plan and optimize up to that point, or execute up to that point, and then re-optimize the rest of the query. Any questions on all that? This can be really interactive, unless you don't ask questions. Question? So if you can use the mic, that helps.
With solid state storage getting so fast, is the sort of the boundary between memory access and disk access, is that kind of getting less? Like for you mentioned tempDB spills, for instance.
So as the classes of storage get faster and faster, so you have really fast SSDs, there's actually exotic non-volatile RAM, which sits in DIMM slots like memory, but is persistent, and that can be accessed as if it were a disk. So that's really, really fast. You're still going through the whole I/O stack, and there's still a lot more SQL code you're going through to write to what we think is a disk. So it's still going to be a lot more overhead than if we just access something out of memory. But you're right that it is getting faster. But you guys are pushing us harder too, so. So interleaved execution candidates. Select statements, obviously. Depends on the 140 compat level. Multi-statement TVFs not used inside of cross-supply. So cross-supplies we're not going to go into with that way because it just gets way more complex. When you're not using plan forcing. If you force the plan, we can't do anything about it, right? We're not using forced parameterization and not using use hints and disable parameter sniffing, right? So if you're forcing how we do the optimization, we will respect that, but that ties our hands to fixing the problems in other ways. Expected overhead is minimal. We're already materializing the multi-statement table value function, so as we accumulate the results, we have it in an in-memory store that looks like a table. So we've materialized it, and so we're just looking at that materialization to see how many rows it actually has. Cache plans, the first execution of a plan will be cached and it'll be used by subsequent execution. So you can end up with parameter sniffing type of issues. Plan attributes, we've contained interleaved execution candidates and is interleaved executed are new attributes on the plan, so you can see that we're actually doing this stuff. We're trying to make all these new features and behaviors more visible all the time. And there are also X events, so you can monitor this. If you're using X events in your telemetry, you can get really fine-grained information out of X events. But we're also trying to surface them in more visible ways like the plan. The plan. A question? Do you see the interleaved execution events as part of an X event? I believe so, but I'm not positive.
Yes, you do. So if you start up the X event session, I'm not sure what's the name of the interleaved X event, but once you enable it and you set watch live data, you should be able to see whenever interleaved execution happens.
So batch mode memory grant feedback. Again, this is a 2017 feature. And the problem is there's times when for every query, we have to grant ourselves memory to work in. We have to have scratch space in memory. If we overestimate the amount of memory that we're going to need, we're going to starve all the other queries. If we underestimate, we're going to end up spilling to disk. And that's all driven by poor cardinality estimation. What we've done to get around that is sort of sidestepping the cardinality problem, because we're not going to solve it in every case right now. But what we've done is introduced a feedback loop into the memory grant mechanism. So the first time, or as you execute a query, we'll note how much memory we requested and how much memory the query ultimately needed. And if there's a big enough delta, we'll record how much was actually used in the query plan that we cache. So the next time that query is run, we'll use that new memory grant value and adapt it. And we'll adjust back and forth a couple times, and then it usually comes to a steady state pretty quickly. Batch mode, so that also was in SQL 2017, it's batch mode. It's restricted to batch mode queries. Also in batch mode, we had adaptive joins. So one of the decisions that we make on physical algorithms is whether you're going to do a join in hash mode or nested loops. So there are different points where each one is more efficient, and sometimes we get it wrong. So what adaptive joins are doing is that we've set up some heuristics as to where that crossover point is in terms of the number of rows coming into the build side, I think it is.
Yes.
So we'll start accumulating the rows for the build side. If the number crosses that threshold, we'll flip that into a hash join. If it doesn't cross the threshold, we'll keep it as a nested loop. So on the fly, at execution time, one execution may turn into a hash join, another execution into a nested loop for the same query. So it's building that. That's one of the classic adaptive techniques we're using. So that was all history. That's all what we did in 2017. Coming in 2019, I can say that now, we're broadening the scope. So where in 2017 these features were mostly adapting to what we saw during execution, we're now broadening to more scenarios. And for a while we kept calling it adaptive QP, and we started getting grief because, well, that feature is not really adapting to anything, it's just making it smarter. So we now have intelligent QP. This is kind of the big picture, and so we can spend a few minutes looking at this. This is how we view intelligent QP and the features underneath it. The parts in the light-face font are the parts that were landed in SQL 2017. So you have your adaptive QP with adaptive joins, interleaved execution, memory grant feedback. Those are both in batch mode only. So all those are things that we've talked about just now. What we're announcing now, today, for SQL 2019, is we're extending memory grant feedback into row mode. Table variable deferred compilation. So we had multi-statement table variable functions for iterative execution. Now we're deferring compilation on table variables until we have a good value on them. Batch mode in row store. So how many people have used batch mode joins and been really happy with the performance? Okay, how many people have been frustrated because you couldn't do it if you didn't have a column store in the query? So batch mode is really efficient. We'll get into a good description of it, but it, until now, has been only available if you have a column store somewhere in the query. And with 2019, we're making that mode available when you have row stores. Approximate QP is a new area where it's about cases where you have huge cardinalities and you're doing aggregations like count distinct is the first one we're doing. If you're doing count distinct across 10 billion rows, it's going to take a while, and it's going to take a lot of memory. So what this does is it gets you an approximate answer with a small fraction of the memory in a very small fraction of the time. So if you're driving, say, a dashboard or something where the precise value isn't as important as being responsive, this is really nice functionality. So memory grant feedback for row mode. In SQL 2017, we introduced batch mode memory grant feedback. We updated the cache plan for row mode spills to disk, row mode excessive memory grant waste, adding new query execution plan attributes to understand the state of memory grant feedback. This is all under the 150 compat level. So what we're giving you to understand what we're doing behind the scenes, we have X events. So we have memory grant feedback loop disabled. So if we're adjusting the memory grants and it goes back and forth and back and forth and back and forth and it's not converging, we'll just stop adjusting because there's no point. We're going to get it wrong 50% of the time anyway. Memory grant updated by feedback is when we're adjusting it and refining our memory grants, and so we'll give you information about that. New plan attributes. Is memory grant feedback adjusted? So did we adjust the memory grant for this plan? And that has several values. So there's no accurate grant, so we didn't adjust it because we didn't have to. No first execution, we've got nothing to base it on. This is the first time we've seen that plan. No, feedback was disabled because you were just oscillating. And then yes, we can be either yes, adjusting, so we have adjusted it and we're in the process of still adjusting, or yes, stable. So we've reached a steady state where it doesn't seem to be moving anymore, so we're just calling it good. And we also have last requested memory.
Yeah, just backing up on the previous slide, where you have a deferred compilation, how is that reflected in the show plan?
So the question was, if you have a deferred compilation, how's that reflected in the plan? Do we have that?
So currently, no, we do not have X events or show plan attributes to show that table variable deferred compilation actually kicked in. But yeah, we love to hear feedback. For example, even for memory grant feedback for batch mode, we just had X events, and customers were like, is there a more intuitive way of seeing this? And we added the show plan attributes. We'll definitely probably look like for upcoming release, we might add something, but currently there's no way of.
So does it just stop there, or does it make some assumptions as to how it, based on old estimates, or?
So the question was, does it just stop there, or what?
Well, I'm saying you have a show plan, and you're
Right.
joining to some table variable.
Mm-hmm.
You would
So-
usually see how many estimates.
So basically, it's basing its estimate on the actual number of rows. So it's going to defer the compilation till we run the table variable.
But if you just did a show plan without an execution,
Oh, you're talking about the estimated plan then.
if you're just doing a show plan, you don't have any actual numbers.
So if you haven't,
Is that table variable?
It will still take the estimated guess count of one row.
Okay.
Okay.
That won't necessarily be the same as what it actually used.
No.
so again, this is the estimated plan, which is before we actually see the data.
If you use a live plan, presumably that's the same.
I'm not positive on that.
It doesn't stop it from doing the optimization.
No, it's
No,
not.
no.
None of this will stop it from doing optimization. This is just what we let you see about how it ran. So now we get to see what this looks like. So number 7 is you.
Okay. So before I jump into the demo, I'll quickly introduce myself. I'm Sri Chintala. I'm an engineer on the query processing team for Azure SQL Database Engine. And I've been with the team for about 2.5 years now. And I've actually been heavily involved with some of the adaptive and intelligent QP features Kevin was just talking about. For example, I was an engineer for adaptive join, batch mode memory grant feedback. And recently, I've been working on row mode memory grant feedback, which is now in public preview and is under compat level 150 on CTP 2.0. So let's look at the demo for row mode memory grant feedback. So for purpose of all the demos, we'll be using the wide world importers DW. And right now, this feature is available only under compat level 150. But going forward, say by SQL 19, we hope to remove the compat level requirement, as this feature does not necessarily alter the shape of the plan, as all we're doing is correcting the memory grants. We hope to make this available to all compat levels. This is especially exciting because if you look at the Azure telemetry, we see about 3 million queries which are spilling or which have overestimates per day. And without the compat level requirement, it's like 3 million queries benefiting, which will benefit from this feature. OK, so I'm going to set this to compat level 150. OK, and we're going to free the proc cache. But usually, doing any scope configuration setting should do that. But I'm just doing that for good measure. So basically, this database is a typical star schema we have, where we have a fact table with a bunch of dimension tables. So these tables, for example, this fact table probably has a couple of million rows in it. And I'm going to fake the statistics to thinking that it has one row. Again, don't do this in real production workloads. It's going to give you a bunch of bad plans. So this query here is where we're going to get a hash join. And then we're using the order by clause, which is going to give us a sort operator. Again, both hash join and sort are memory consuming operators. And since we faked the statistics to thinking that the table has one row, it's going to get a wrong memory grant, or it's going to be given very little memory, and we should see it spilling to temp DB now. So this query is probably going to run for a couple of seconds. And in the meantime, I would like to talk some more about the show plan attributes. So previously, the way you would know memory grant feedback kicked in is to enable X event session. And then when memory grant feedback kicks in, you see the live data coming in. So based on like some customers are like, hey, X events are cool, but then you have to go, you have to start a new setup wizard, you have to watch the live data. Is there an easier way to see this? And now we have new show plan attributes, which I will be showing in a minute. So let's look at this plan. So clearly, both hash and sort operators spilled. That's because it estimated one row, and actually it got about 3 million rows. OK, so the attributes I was talking about, so if you look at the properties, at the memory grant info properties, you have this property called is memory grant feedback adjusted. And currently, its value is no first execution, because the first time you run the query, we're just going to track the usage. How much memory did the operators actually need? If they spill to disk, what is the memory it actually needs so that we prevent the spill the second time? So the second time you run this query, memory grant feedback is going to kick in. And based on the usage, we're going to give it the memory it needs so it does not spill. And also to notice, it took about 29 seconds for the query to complete. That's because it had a temp DB spill, and temp DB spills are quite expensive. OK, wow. OK, so that took about 3 seconds. So that's almost 10 times faster. And so now if you look at the attributes, OK, where's this? OK, so if you look here, now the attribute changed to yes adjusting. So that means feedback kicked in and feedback was applied. So if you run this multiple times, in this case, probably if I run it again, it's going to reach a point where it says yes table. That means memory grant feedback kicked in, it was applied, and at this stage, it has the exact memory that it needs, and we're not going to change it anymore. And there's also this case where memory grant feedback could be disabled. For example, you have parameter-sensitive plans. This is a non-goal for memory grant feedback, because if you have parameter-sensitive plans, it's going to fluctuate. So if for the first time, you have a parameter which gives you very low rows, and the second time you have you pass in a parameter which returns 1 million rows. So it's going to cause fluctuations. And at this point, after 32 executions, memory grant feedback like, hey, I'm not helping this query. At every execution, I'm giving it more memory. I'm going to reduce the memory, and you keep increasing and decreasing, and we're going to oscillate. And after 32 executions, we're going to disable the feature. At that point, this attribute is going to read no disabled. That means the feature was not helping your query. That could be one of the scenarios. The other scenario could be that for some other reason, even though it's not a parameter-sensitive plan, even if it's a static query, for some reason, due to some bug, it could be no disabled. That's when you know something's wrong. You can reach out to us, and you'll report an issue. And some of the other parameters you'll see is no accurate grant. So the query got an accurate grant in the first place, and there was no need for memory grant feedback to kick in. OK, yeah, what else? I think that's about it. I'm going to set the statistics back to its original count so I don't mess up the rest of the demo. And you can continue.
Yep. Thanks. This really nicely illustrates kind of the hallmark of this suite of features that we're working on. What we're going here for is features that make things run faster without you having to do more work, right? You notice that we didn't touch the query at all. The query ran the first time, it ran in 29 seconds. Run the same query again, exactly unchanged, against the same data, it went from 29 seconds to 3 seconds. That's the sort of features we're working on, is features that will just make it faster without you having to rewrite anything to take advantage of the features. So table variable deferred compilation. The legacy behavior for manual stats creation and update temp tables, you can do manual stats creation and update. Table variables, you can't. Makes sense. You can create indexes on temp tables. With table variables, you can only create indexes that are in line with the table creation definition. Constraints you can put on temp tables. For table variables, only a primary key, uniqueness, and check constraints. And again, as part of the creation of the table variable. Automatic stats creation happen with temp tables. They don't happen with table variables. And finally, creating and using a temp object in a single batch. So if you create it and use it in the same batch, for temp tables, compilation of a statement that references the temp table, it doesn't exist, is deferred until the first execution of the statement. So if you reference a temp table that has been created within that batch, we won't compile that statement until we've executed everything up to that. So we can get a decent handle on the number of rows to expect. With a table variable, in that same situation, we'll give you a fixed estimate of 1. Because we don't really have a way to stop in the middle of that statement to pause and re-estimate. So the change here is that with table variable deferred compilation, which again is part of the 150 compat mode, and that's the only thing that you have to change, is you upgrade to 2019 and turn on 150 compat, and this behavior turns on that compilation of the statement that references a table variable that didn't exist is deferred until the first execution of the statement. So again, it's like the interleaved execution. We're waiting until we get to that statement and have a count of how much data is in that table variable before we compile statements that reference that table variable. And we can now see it. So 7 is demo, 5.
Okay. So for before table variable deferred compilation, so how this worked is, so if you had a query or if you had a procedure with a bunch of statements that reference a table variable, during the initial compilation and optimization stage, we just estimate a guess count of 1 for the table variable, which is kind of okay if the actual number of rows returned by the table variable are pretty low. But if, say, it returns 1,000,000 rows, then your estimate is completely off. And this is a problem because, say, if you have a table variable here and then you have a bunch of operators downstream, all of them are going to propagate an estimated row count of 1, which is going to affect the plant quality during optimization, because some of the most of these decisions are based on the cardinality estimates, such as which join algorithm do we use? Do you use a nested loop join or a hash join, or do we need parallelism? So all these decisions are affected by these cardinality estimates, which were off previously before this improvement. So how did we get around those? So the way we got around the wrong or the guessed estimate was by using option recompile, or we instead used temp tables, or we forced the join hint, like we would say option hash join or option nested loop join. But with the table variable deferred compilation, you don't have to do anything. This feature will fix the problem for you. And currently, this is under compat level 140. So first, I'm going to set this to 140 to see the behavior without the improvement, and then we're going to see what are the benefits we get when we enable it. Okay, so use master. Okay, so we're declaring a table variable called order, and then we're going to reference it in our query. So this is probably going to run for a couple of seconds. And it's kind of interesting. If you look at the plan shape, you can tell me what you see now, and then just remember what you see without the compat level 150 and the feature, and then you can tell me what difference you see when the feature kicks in. So let's look at the plan. Okay, so this is our table variable. We see that the estimated number of rows, it estimated a row count of 1, which is default. And the actual number of rows it actually got is about 3.5 million, so which is way off. And what else is wrong with this plan? Any inputs? Somebody said something? Yeah, the join type. So if you you can see, it picked the nested loops join, which is kind of not a good choice because we have like 3.5 million rows. So the higher the number of rows, a hash join would have been better. And you can see that the sort has spilled. This is kind of intuitive because it estimated a row size of 1. We gave it way too less memory, and then we have a spill to temp dB. And you can also see that you don't have parallelism in this plan. Let's rerun this on compat level 150 and see what we get. And also, just to point out, this query took about 19 seconds. Let's see if it gets any better. OK, I'm just going to set this to 150. And I'm using exactly the same query. We're declaring the same table variable and using the same query. But yeah, like somebody asked, unfortunately, we don't have a way of seeing that the feature kicked in until it does, but hopefully we'll have some X events or show plan attributes for the next release. OK, let's see. So first very interesting thing is the table variable has been flipped. Now, before it was on the build side, and now it's on the probe side. So let's see. The actual number of rows is way better. The estimated number of rows is actually correct and way better than the estimate we had last time. And the join algorithm is correct. Instead of a nested loop, we have a hash match. And then we don't even have the spill anymore. So by having this feature, we are avoiding a bad plan. We are improving the plan quality and, in turn, improving the performance. And it took about 9 seconds. Yep.
Yep. So again, it's another example of making things faster without having to change anything.
It did not go through. Okay.
So prox count distinct. I said a little bit about that at the outset. What this is doing is it gives an approximation of the exact answer. It uses a very small fraction of the memory. It's very fast. It uses a technology called hyperlog-log. It's a way of doing a sampled estimate of what the actual result should be. And the results are going to be within 3% of the precise answer for 97% of the cases. You can construct convoluted cases that will break the algorithm and give you an answer that's way off. But in 97% of the case, it's going to be within a very small margin. And again, this is not for financial results. Something where the precise answer really matters. Obviously, you're not going to use approx.
What's approximate balance in there?
What's the approximate balance in your checking account? But for cases where responsiveness is way more important than the last couple digits of precision, this makes a lot of sense. So if you're driving a dashboard where you're driving a needle, the last couple digits, nobody's going to ever notice, but they're going to notice if it hangs there for 30 seconds before it updates, right? So this is the sort of thing where this really makes a lot of sense. So this is a syntax change. So there's no compat level requirement because you have to opt in by using the new syntax. So instead of count distinct value, this is now approx count distinct of the value. So a very minor change. Inside the expression, obviously, it's anything you could feed to a count distinct. And let's see what that looks like. 7.
Yep. OK. So basically, approx count distinct evaluates the given expression and returns the approximate number of unique non-null values in a group. Again, it's approximate. And like Kevin said, it's plus or minus 3%, 97% of the time. And so one of the main reasons you would want to use this is responsiveness. And the second thing is it has a very little memory footprint. So count distinct is a very exhaustive operation. And most of the time, if you've noticed, it causes spills to temp dB. Whereas approx count distinct, you're going to see it. It's like magic. It's like probably 300 times less memory than what a count distinct would take. So it has a very low memory print and, in turn, great responsiveness. So for example, dashboards, and even if you're a data scientist, where you don't need to know the entire data set, but just a gist of the number of values in your data set, this would be like a perfect example of where this would come in handy.
The lower memory usage means not only are you not spilling and causing a big delay that way, but you're also not starving other queries. So even if we didn't spill, you're using a lot more memory than you need to, and by using a smaller memory footprint, you're giving a lot more memory to other queries.
Anywhere you don't need it to be exhaustive and precise, this would be a good thing. And like if you see in my query, I'm using this hint, disallow batch mode. This is because I don't want to steal the thunder from batch mode on row store, which is another improvement, under the intelligent QP tree. So here, just to isolate the two perf impacts, I'm disallowing that feature. Otherwise, this query would have run in batch mode. So let's see, I'm just going to run this. And this is the count distinct version, which is going to return a precise value. And probably going to take a bit of time because it's memory intensive. Again, so if the perf gain you're going to see depends on what type of query you're running. So if your count distinct is actually going to fit entirely in memory, probably you're not going to see a lot of perf gain. But if especially when it spills to temp DB, you're going to see the real difference. So let's see. So this, it says it has about 29 million distinct values. That's the value it returned. And then let's take a look at the memory. So, OK. Properties. OK. So granted memory was about 1.5 GB. Somehow in this case, we don't have a temp DB spill, which is good, but it still took a lot of memory, a 1.5 GB of memory, and it took approximately 12 seconds to run. Let's rerun this with approx count distinct and see if we're within our error rate and what the execution time and the memory look like. What did you say?
You should clear cache before you.
It's a different query
It's because we're using
the approx count
it's a completely
distinctness.
different function. I can clear the cache and rerun it for you just to prove it, but it's a completely different query, so I don't think it should affect that. OK, so it finished in about 5 seconds. And then let's look at the memory info. If you see, that's literally not even 100 KB from 1.5 GB to 72 KB. And it estimated, like it said, there's approximately about 30 million rows. So we're off a bit, but that's still not an issue, especially if you're using this for a dashboard. Since you asked, I'm just going to clear the proc cache and do it again, just to show you that it's completely different query. OK, where's this? OK, have it somewhere. Yeah, there you go. I'm going to free the proc cache. And let's rerun that query. OK. Oh, and by the way, anyway, it had recompile in there, so it would not. OK, I run. No, we're good. OK, let's see. Yep, still the same performance. 30 million rows. And we should, yeah, it should still be a relatively less memory print. Yep.
Same memory, Grant.
Yep. OK, going back to you, Kevin.
Are there any other questions up to now on the stuff that we've talked about?
Or the demos.
Yeah, so this is approximate count distinct is one of the exceptions, but in the general case, what we're looking at is features which don't require any change to your code. You don't have to do anything to adopt it, just runs faster. And that's why you see them tied to the compat level. So anything that can change the way we optimize a plan or the shape of the plan, performance, without you changing anything in your code is going to be tied to a compat level. That way you can upgrade without worrying about things changing underneath you suddenly. Question?
I have some nasty multi-statement functions. Would any of the stuff that we've discussed help those?
So you have some nasty multi-statement functions. Are they table value? So multi-statement table value functions, yes. We've got some help for you there. I had something in mind, but it's gone.
Yeah.
You mentioned it doesn't work in cross-apply, because that applies to out-apply as well. So it's table value functions in front that is not in cross-apply or out-apply.
Right.
Is that right?
Yep.
So again,
Kevin wants, they had a question.
Without getting too deep into the secret sauce, could you tell us how you set that up? Like, I'm kind of intrigued how you got the row mode, just it must have made something structured to optimize the approximate.
So-
The approx count the same.
a prox count distinct. It's mathematics that's way over my head.
It's hyper log log.
But the Cliff Notes version is that what they're doing is using a fairly sophisticated sampling algorithm. So they're getting samples within certain ranges of the data set, and they've got ways, the secret sauce is in figuring out which are going to make it representative and give us a good example. So they only have to digest a smaller amount of data without going through every row.
The entire data set. Sure.
So prox count distinct is useful for cases that have very large data sets. If you can fit it in memory, you're not going to gain as much, if at all. Don't require complete precision, right? You're not betting the farm on the exact answer. And do require fast response. Not appropriate for situations that require precise answers, financial results, et cetera, or have small data sets. And it's important to understand that a prox count distinct isn't a magic, it'll always go way faster answer. Because if you're not running into the problems that this solves, it's not going to solve anything for you, right? So if you're not running out of memory or starving memory because of the amount of memory consumed by the count distinct, then you're not going to have, this isn't going to improve matters much for you. Question?
Will the count distinct not get faster the more times you run it?
Will the count distinct not get faster the more times you run it? It's always going to take that much memory, and that's typically what you're going to be bottlenecked on.
So probably count, like memory grant feedback would have helped. Like if you execute it a second time, we would have probably fixed the spill, but it's still going to take all that memory. It needs that memory because it's an exhaustive operation.
So basically, you're building a hash table of every distinct value, and when you've got millions of distinct values, that gets to be a really big data structure, and it's going to chew up a lot of space. So batch mode on row store. So batch mode processing is something that came in with column stores when we started having column store indexes. Column stores are nice because they're very compressed, they're very efficient at handling lots of data. Batch mode processing came in with those. They both tend to work in analytic queries where you're scanning lots and lots of data, and you're doing typically aggregations, sums, averages, things like that. Row store moves one row at a time. So you're moving one row through the whole plan, flows through. Batch mode flows data about 1,000 rows at a time. You make a batch of about 1,000 rows and flow that through. And so instead of, for an average operator, you add one more one more value into the average, and you add another value into the average. We're adding 1,000 rows in one operation using vector ops within the processors. So it gets way faster. It's much, much more efficient, but it has been linked with column stores. There have been some notorious MVPs who have found ways to trick the optimizer into using batch mode, even though they weren't using column stores in the query, by having a column store table index in the query that didn't really take part in anything. It was just there to force the optimizer to think it could use batch mode. So rather than having people invent these convoluted workarounds, we figured we'd give you a way to use it up front. So this is really useful in HTAP scenarios, so hybrid transaction analytical processing. And that's where you're doing analytic queries across a data set that is also a live OLTP table. So order processing table, that sort of thing. you sometimes want to do analytics across that. Inventory predictions, so if you're doing predictive intelligence, BI sorts of operations, you want to know, okay, when am I going to run out of this piece of inventory? Canonical example I use is flowers. You're selling flowers. You'd want to know if you're going to run out at the end of the day, or if you're going to have a bunch of flowers left over that are going to wilt before tomorrow, or if you're going to run out before the end of the day and then lose all that opportunity of people that might come in later wanting to buy them. So it's a perishable commodity, and that's just one example of where you need to get predictive results, analytic queries across your live data. It doesn't work to do ETL out and analyze it a couple hours later. So that's kind of the scenario where batch mode on row store comes in. There's some cases where you can't use column stores. So batch mode is very efficient at doing aggregations on large set of rows. Created column store work, use cases overlap. It's also helpful where no column store exists. So this is just kind of a graphic that I showed that illustrates the difference in how things get processed. So here you see a row mode. So each row sequentially goes through all the operations in the query plan. Batch mode for column store, you have each of the columns is in its separate store, and we'll pull 1,000 rows out of that and flow them through all the operations one by one. But it's in that whole group of 1,000 row moves as one unit through all the operations. With batch mode for row store, we can do the same thing. We're taking 1,000 rows, so it's all the columns, and unlike column store, where you can avoid referencing columns that don't take part in the query. Row store, you're going to take all of them, and that group of 1,000 rows then will flow through all the operators in the query. So this is kind of the conception of what we're doing here. So again, this is a 150 compat issue because it does change the shape of the query. Query optimization, batch mode heuristics. So what we're doing is allowing the optimizer to consider batch mode plans when there's not a column store present. So we're opening up the search space. The optimizer for a given query is going to search through all the possible ways it could solve that problem, right? It's going to search through all the different paths it could take to get an answer to a given query. And by adding in batch mode, that just exploded that set of possibilities it has to explore and evaluate which one's going to be the most efficient. So there's a cost to that. So we've put in some heuristics up at the top to avoid going down those paths if it's obviously not going to be a win. So we're going to look at table sizes, operators used. If it's small tables, you're not going to gain anything by batch mode, so we won't go through the extra overhead of exploring all those plans. Estimated cardinalities in the input query. We have additional checkpoints as we're going through optimization where if all the batch mode plans are coming up with much higher cost than what the row mode plans are, we'll probably stop evaluating batch mode plans. Before we put those in, we had cases where we were able to speed the actual query execution up marginally with batch mode, but the extra compilation time way overshadowed any gain we got in the execution time. So that's what we're trying to avoid here with these optimizations. We've also given you a lot of controls, so you can force batch mode off. You can enable it, but it will never be forced, because if the optimizer finds a faster way to get your plan done, it's going to do that whether it's batch mode or not. So we also introduced a new batch mode scan operator. So the scan operator is the part of the query execution where it actually reads the data out of the data pages or out of the column store and starts feeding that pipeline of data. And so now all the way down at that end, we're forming batches. So the scan operator reads rows makes a batch of 1,000 at that point, and everything past that is running in batch mode. So it gets as efficient as it can possibly be. What might benefit from this? If a significant part of the workload is analytic queries, queries with operators such as joins and aggregates processing hundreds of thousands of rows and more, and the workload is CPU bound. If you're completely I/O bound, then what we do with the CPU isn't going to change anything. And the recommendation there is to, if you possibly can, to add a column store, because column stores reduce the amount of data that you actually have to flow through. So you're drastically reducing the I/O you have to use if you can use column stores for analytic queries. Typically, we get 90% compression out of a column store, so it's 10% of the size it originally was. And you also only look at the columns which take part in the query. So if you've got 1,000 columns in your table and 5 of them take part in this query, you only have to read 5 columns off of disk because each column is in separate physical container. So creating column store index adds too much. So if creating the column store index adds too much overhead to the transactional part of your workload, or if you're doing a lot of churn, that's going to degrade the column store. If it's not feasible because your application depends on a feature that isn't supported yet on column stores, obviously you can't use them. So those are cases when you would not use them. So now we have a demo. Show you what it looks like.
Yep, again, this is in, sorry, I keep forgetting. Yep. Again, this is a feature which is tied to compat level, so we have it under compat level 150. So again, for the purposes of this demo, I'm just pointing out that we do not have a column store index. So if not for batch mode and row store, the way this query would have executed would be in row mode, which I'm going to show you now. So for example, you're a user and be like, hey, I don't want my query to run by default with batch mode and row store or with batch processing. So we have a disallow batch mode hint where the user can explicitly choose to disable batch mode processing. So I'm going to use this hint so we can see what the performance looks like in row mode. And again, before we build a feature, we look at the telemetry. So who is this improvement we're going to build going to benefit? And from the telemetry, most analytical workloads benefit from batch processing. And the requirement was that they needed a column store index. But now, OK, so let's see. So you can see that it's row mode. All of them are. You can see all of these operators are running in row mode. OK, and then let's look at the elapsed time or the performance.
11 seconds.
Yep. OK, 11 seconds. Let's rerun this. So without the hint, by default, it's going to run with batch mode on row store. And hence, we're going to get batch processing.
$11 down to 3 seconds.
Almost.
That's the difference that batch mode can make.
4x, that's a 4x improvement. So let's see. So like you can see, all of these are now batch execution. And another interesting thing I want to point out is the storage is row store. So you want to explain what that means, Kevin?
So that means that the storage was the source of the data for here was a B tree or a heap. So classic row store table, not a column store. So we know that the data was coming out of a row store, but being processed in batch mode all the way from the physical scan.
Yep, I think that's what we have for the demo.
OK. So any questions on batch mode and row store?
We have a question.
Yes.
How much expensive is this? I run in Azure SQL, right? And I have GPUs. How much expensive it is going to be?
So how expensive is it going to be?
Yeah, on my research.
These features generally save you resources. That's why they go faster, so it's going to be less expensive.
So when I say expensive in terms of if I look at GPU, it's not just CPU, right? CPU, I/O, and then memory.
Right. So
God, if I'm not processing 1,000 at a time, and probably it's going to do parallel as well. So if it does batches of 1,000, will it also say, let me start parallelizing my batch queries, and potentially it can eat up all the resources there?
So the question is, if you're moving these batches of 1,000, you've got these bigger chunks of data moving through, and you're probably going to enable parallelism, so you're doing more of them in parallel. Isn't that going to chew up more resources and cost me more? Actually, no, because you, for a given number of DTUs, have a set amount of memory. You don't pay more if more memory is used. It's not going to use significantly more memory to do batch mode versus row mode, and it's going to use a lot less time and processing overall. So you can use a lot less CPU to process your data. The other thing to note is that we're shifting the way we sell Azure data, SQL database. So it's been DTUs all along. We're introducing a new model. It's called the vCore model. So now we're splitting out CPU and memory and other parameters. So you can tune the number of cores separate from the other parameters. The idea is to make it a lot more flexible, because we have some customers that need lots of CPU but have a fairly small data set, or vice versa. And so we're giving you the flexibility to buy what you need. So those won't be tied in the future. The other thing to comment on now that we brought Azure into the picture, this was described under Azure, but it's all the same code underneath. So it's important to understand that we have one code base for SQL Server, Azure SQL Database, Managed Instance, all of those. The SQL engine is the same code. So what happens is that when you load a standard edition license, you get one set of behaviors. If you load enterprise edition key, you get a different set of behaviors. When we deploy in Azure, there's a slightly different set of behaviors, but it's all built from the same code. We refresh the bits in Azure about once a month. And that's why we're so hardcore about tying things to compat levels so we don't disturb anybody, because that just happens invisibly. You get new code, things get better, hopefully. And this is how we keep things from getting worse. So you have to opt in to changes that might give you poor query performance. And then every year or two, or however long the cycle is, we'll take the current set of that same code and ship it to you as a version of SQL Server if you're on premise. But again, that's the level of compatibility, and I think that's really a differentiator in the marketplace, because we have the same code whether you're running the platform as a service or infrastructure as a service in VMs or on-premise. It's all the same query engine, so it makes it really nice, compatible story going across the board. Yes, managed instance will be updated the same way, because it's all part of the Azure infrastructure. Yep. Question?
Yeah, and if it's not too long, can you just tease out the instance where you have a small enough data set to make disabling batch mode more effective? Yeah, the kind of fraction issue. It sounded like you had some examples where the time to evaluate with the extra options for batch mode were greater than the performance gains by using that.
So the question is, help me understand the cases where why batch mode would be less effective. So the issue is that the optimizer has to evaluate every possible plan to see what's going to be the cheapest plan to use. And by turning on batch mode as a possibility, you just multiplied the number of possibilities it has to evaluate. So it's going to take more time during the optimization phase and compilation. That's kind of a fixed tax. And so if it takes 10 seconds to do the optimization and your query execution time went from 3 seconds to 2 seconds, you still lost. So that's kind of the idea there. Okay? So that's what we had to talk about intelligent QP. There's places to get more information. I'm available for questions as well. Shri is as well.
Yep.
One other piece, we have a program called Fast Track to Azure, which is if you're migrating to Azure, we've got a practice that will help get you there. Proven practices, we have expertise from Microsoft, we'll pull expertise wherever we have to get it, from design, configuration, development, to deployment, to migration. All of that you can get help with azure.com/fasttrack. Okay, thank you.